Today we're going to be working through some what we call optimization problems, where we're going to be given a situation and we are going to either maximize it or minimize it. So here's kind of a general procedure to follow. If there's a diagram to be drawn, to draw the diagram and label it with the variables that you're going to use. Find a formula for the quantity that's supposed to be maximized or minimized. We're going to then there will be some additional information that we need in order to solve the problem. We'll see if there's any restrictions based on the situation. And then we will use calculus to find our solution. All right, so our first problem. A rectangular corral is to be built alongside of a long building. If 100 feet of fencing is available, what dimensions should the corral be to maximize its area? All right, so first we'll start with a picture. Okay, so let's say that's our building, and we're going to be building a fence alongside that. Okay, so this is our corral. I'm going to label this dimension x, which makes this x, which makes this y. So you can start with the function that you're trying to maximize, or we can start with our known information. So I'm going to start with my known, that I have 150 feet of fencing. So I have 150 feet to put along these three walls. So for the fence, x plus y needs to equal 150, or 2x plus y equals 150. Then we're going to look at what we are trying to do in this problem, which is to maximize the area. So write a formula for the area. The area of this is just going to be x times y. So that's the equation that we are trying to maximize. But the first thing that we need to do is put this all in terms of one variable. So I'm going to come back over here. Should have been a 2x, and solve for one of the variables so I can replace it. So I'm going to say y equals 150 minus 2x. I'll take that and substitute it in over here. So a is going to equal x times 150 minus 2x. Do a little bit of simplifying. 150x minus 2x squared. Okay, so technically we would need to find the maximum, look at the end points and the critical points. For this one though, the maximum is going to occur at a critical point, and I'll illustrate that here. So to find the critical point, we're going to take the derivative. So a prime is going to be 150 minus 4x. Critical points are going to be when the derivative is equal to 0. So 4x equals 150. So x equals 37.5. Okay, so x, the dimension perpendicular to the road, or to the building, is going to be 37.5. The y then, along parallel to the road, is going to be 150. We'll plug it back in here. So 150 minus 2 times 37.5 gives me 75, and that will be parallel to the building. But if you have a good diagram, that's usually good enough for me. So 37 in that dimension, 75 in that dimension. The way you could justify that this is in fact the maximum is if I took this derivative, I'd get -4, which means the second derivative would be negative, which means the graph would be concave down, which means the critical point is a maximum. And also just picturing this is an upside down parabola, so the maximum is going to occur at that vertex. Our second example, you have 1,000 feet of fencing to enclose a rectangular playground and subdivide it into 2 smaller playgrounds by placing the fencing parallel to one of the sides. What is the largest possible area of the playground? So we're going to have a rectangle and they're subdividing it into 2 areas. So you can label this in different ways if you want to, but I'm going to label that X, and I'm going to label these sides, the whole thing, as Y. And again, you can start with what you're trying to maximize, or we can start with my known. So that's what I'm going to start with. So I have 1,000 feet to build this thing. So 1, 2, 3x plus 2y is going to equal 1,000. I'll come back to that equation in a minute. We'll write equation for the area. Okay, well the area is still going to be for this one x times y. We want to get this in terms of one variable, so I'm going to take this equation and solve. And you can solve for either x or y, it doesn't matter. And then we'll divide by 2, so that'll be 500 minus 3/2 x. We'll take that and replace it over here. Simplify it, and then we'll take the derivative. Okay, so again we have an upside down parabola, so the maximum is going to occur at the critical point. So we'll take the derivative. Okay, so we get 500. If I multiply 3/2 times 2, we get 3. So we set this equal to 0 to find the critical point. So 500 divided by 3 is approximately 166.667 feet. The y value then is going to be 500 minus 3/2, so we're using this, times 500 over 3 is going to give me 250 feet for those 2 dimensions. Okay, it also says what is the largest area. So these are the dimensions that are going to give me the largest area. The area is going to be the product of those 2. So I'm going to use the unsimplified. So this is going to be approximately 41,666.667 feet squared is the maximum area. And sometimes they'll ask for the dimensions, sometimes they'll ask for the maximum area, sometimes they'll ask for both. Okay, our next problem. A farmer wishes to fence in a rectangular pasture 1 square mile in area. One side along the road, the cost on one side along a road. The cost of the fencing along the road is higher and equals $5 a foot. The fencing for the other 3 sides costs $3 a foot. What is the shape of the most economical pasture? So let's draw our situation. Okay, there's our road, and we're going to draw another square. I'll call this X, I'll call this Y, and we are fencing this side as well. So I'm going to start with my known, and again, you can do this either way. I know that the area is 1 square mile. So x times y is going to equal 1 square mile, but my numbers here are in feet. So I need the square mile to be converted to feet. So 5,280 squared, which is a large 27878,400. So 27,878,400 feet squared. I'll come back to this in a second. So what I am trying to maximize here is cost. So the cost per foot is going to be 5 times this y plus 3 times x plus 3 times y plus 3 times x. So my cost is going to be 8y plus 6x. So that's the equation that I am trying to maximize, but we need to get it in terms of one variable. So we're going to come back over here. I'm going to solve for y again. This time we're going to do that by dividing. So I'll replace that into this y. So we're going to have 8 times that whole thing. And I'll do one simplifying. So if you multiply this number by 8, and obviously you'd get a calculator to do this. 302,7200 over x plus 6x. Alright, so this is our function that we are trying to minimize. Okay, we want the smallest cost. So we're going to take the derivative. The derivative of this is going to be negative that number over x squared, because it's the derivative of 1 over x, and then that's just a constant, plus 6. Okay. If you were to take the derivative of this, you'd end up with a positive this number times 2 over x cubed. So that would mean the second derivative is concave, or the second derivative is positive, which means the original is concave up. So this is going to create a minimum for us. We're going to do that by setting it equal to 0. Equals 6, sorry, plus 6. So 6 is equal to, so we can add this over, so 223027200 over x squared. I can multiply the x squared over, so 6x squared equals this. Divide by 6. That equals x squared, and then take the square root. So my x is equal to the square root of all of that. We're running low on space here. So in the calculator, you would take that and plug that in, and that gets you approximately 6,096.819 feet in the x direction. For the y, you'd come back and plug that number into here using calculator accuracy. So I did, take in your calculator, take this number in its entirety and divide it. So y is going to be approximately 4572.8 0.614 feet. So this is the shape. So along the road and its parallel side, it's going to be 4,500. For the perpendicular, it's going to be that 6,000. Next one, find the most economical shape for a box open on the top so we want to minimize the surface with a square bottom and vertical sides, and it's to hold 4 cubic feet. Draw our box. Okay, so there's our box. I'm going to say we've got a square base, so if that is x, that's x, and then our height is going to be y. So the thing we know is the volume. So the volume, x times y, is going to equal 4 cubic feet. So x squared y equals 4. So y is equal to 4 over x squared. We are trying to minimize the surface area. So we need to write an equation for that. So I'm just going to say SA equals. So the surface area, we have one base because the box is open on the top. So there's one surface that is x squared. And then around the sides, we have 4 identical sides that are going to be x times y. So we have 4xy for the other 4 sides. So we're going to take the y, replace it with this. Simplify it. So 4 times 4 is 16, and then x divided by x squared is going to give me an x in the denominator there. Now we're going to take that derivative. So the derivative is going to be 2x minus 16 over x squared. Okay, again, if I were to take this derivative, we'd end up with a positive value, which means we are, in fact, finding the minimum. So I'm going to set this equal to 0 to find the critical point. So 16 over x squared equals 2x. So 16 equals, I'll multiply over the x squared. So x times x squared is x cubed. Okay, we can divide by 2, so 8 equals x cubed. So x equals 2, so the base is going to be 2 and 2. The y is going to be 4 over 2 squared, so that's going to be 1. So this box's dimension is going to be 2 feet by 2 feet by 1 foot tall. This problem is going to be different than the one that's in your notes, so take a second to change it to this one, and then we'll go through it. So a right cylindrical can needs to have a volume of 1,000 centimeters cubed. What are the dimensions needed to minimize the materials used, meaning minimize the surface area? So if we have a can, there's my can. Okay, there's going to be 2 dimensions that I care about on a can: the radius of the base and the height. So we know the volume. Okay, for my volume, 1,000 is going to equal the volume of this, which is pi r squared h. We'll come back to that. The dimensions, or the surface area, we're going to have the 2 circles. Okay, surface area is the sides, so pi r squared, and there are 2 of them, so 2 pi r squared, plus the sides is, if you unfold it, it's going to be a rectangle. The base of that rectangle would be the circumference, so 2 pi r times the height. Okay, so this is my formula that we're going to minimize. So we need to solve this equation for one of the variables. H is going to be the easiest. So H is going to be 1,000 divided by pi r squared. So my surface area is going to be 2 pi r squared plus 2 pi r 1,000 divided by pi r squared. Again, we'll simplify this before we take the derivative. So if we look at this, I have pi on top and pi on the bottom will cancel. The r will cancel with one of those r's, and then we'll multiply the 2 times the 1,000. So we'll have 2,000 over r. So we're going to take this derivative. So this is going to be 4 pi r minus 2,000 over r squared. We're going to set this equal to 0 and find our critical point. So 2,000 over r squared equals 4 pi r. Multiply over by r squared. So we'll have 4 pi r cubed. Go over here. So now we're going to have r cubed equal to 2,000 divided by 4 pi. So r is going to be 2,000 over 4 pi to the 1/3. Type that in the calculator, and you get approximately 5.419. This will be centimeters. The height, we're going to take it and plug it back, the r that we just found, and plug it into this. So in the calculator, that gives us 10.839. And there is kind of an interesting thing of, this is always the dimensions of the relationship, that the height is always going to be double the radius, or if you think about it, the diameter and the height are always going to be the same on the most economical shape. Right, a rectangle has a base that's on the x-axis, and its upper 2 vertices are on the parabola y equals 12 minus x squared. What is the largest area the rectangle can have, and what are its dimensions? Okay, so we have the x-axis, y-axis. We have an upside-down parabola that's moved up 12 units. So here's 12, so we're just going to draw this parabola. And we're looking to make a rectangle whose base is on the x-axis and whose vertices lie on the parabola. Okay, so depending on where the x is, you can have a real skinny and tall one or a fat and short one. Somewhere in there is one that has the biggest dimensions. So this is going to be x. This dimension, whatever based on x, this dimension is going to be 12 minus x squared. Okay, so the area here, the base of this rectangle is going to be 2x. The height of the rectangle is going to be 12 minus x squared. So the area is going to be 24x minus 2x cubed. We'll take that derivative. set it equal to 0. And solve. So we're going to add 6x squared equals 24. So x squared equals 4, which means x is going to equal positive or negative 2. So we'll just say 2. So the dimensions, the base of this rectangle, if this is 2, that means the base is going to be 4. And then the height is going to be 12 minus x squared, so 12 minus 2 squared, which is going to be 8. So those are the dimensions of the rectangle with the biggest area. Okay, number 7 is like a question that you're going to see in your homework, so you take a look at it. I can help you out with your need. But for the majority of your problems, that will cover it for max and min day 1. We will continue with this for day 2.